because of the remarkable event that we had last week, this is Nobel Prize in Physics on the same subject. So Professor Derrida, myself, decided to make certain deviation from the mainstream, and it will be something like that today. So I hope that it will take a part of the first hour to discuss the essence of the question that was raised by Einstein, Podolsky, and Rosen, and then quite remarkably was solved in a certain part, negative part, the positive way by John Bell. Well, and let me start from a very short reminder on quantum mechanics. In fact, it was discussed on the first lecture, but it was quite short discussion, and we need a couple of the important items of the quantum mechanics which we are going to use. So it is just assume that we have a quantum system which is in a pure state psi, and then let's O be an observable. Then we just, it is a piece of linear algebra, it's a Hermitian operator, therefore bispectral theorem. So we have a Hermitian operator. It is not related to quantum mechanics, but by the way, it was developed by initially Dirac, and then von Neumann made a beautiful theory. I mean the spectral theorem for Hermitian operators. These are eigenvalues, these are eigenvectors. But this is general formula in which you count every eigenvalue according to its multiplicity. But if there is the degeneration, if some certain eigenvalues coincides, then you rewrite this formula in a bit general forms that and OS, these are all eigenvalues, omega t, these are different eigenvalues, distinct, and then you regroup the terms, and the sum of all the rank 1, this projection operator, that correspond to the same eigenvalue, you just unite in the certain, maybe already not rank 1, projection operate projection, and its rank already is equal to the multiplicity of eigenvalue. Then, if you take into account these important things that I didn't mention, because generic eigenvalues are not generated, so the Born rule, which is one of the cornerstones of quantum mechanics, because it relates the theory with experiment. And Born rules say us that if the probability that in the state psi, the variable observable has a value omega t, so your system, you ask the question, what is the probability? Your system initially in the state, pure state psi, and then you ask what is the probability for the system to be in the state psi, t, and the answer is just the diagonal entry of this projection operator with respect to state psi, and it is by this formula you see that it is a sum of this square of scalar products corresponding to these eigenvalues omega t. Well, this is just a reminder, and then let's consider simplest possible bipartite system. This is 2 qubits. That means that every party of the system, there are 2 parties. This is just the simplest, the minimal, non-trivial dimension, just 2. So we have 2 by 2 system, 4 dimension, and we assume that it is system. This system is a state which is known as phi plus, the notation by Bell, and it is just like that. So you have the both qubits there. This is a state. This is a state. Then both qubits are in the state, you see, in that state. And this is both qubits, they're in that state, yes? And in fact, these vectors, they are eigenvectors of very simple operator, matrix, 2 by 2 matrix. So this is, oh, excuse me, this is written here. Well, and as usually, it was again on the first lecture, we write, this notation means that you just take, because these vectors are two-dimensional, your system is four-dimensional, so this is just notation for the tensor product of two vectors. Yes, so this was already not once was written. And then now we assume that our system consists of two subsystems A and B, two parties. And I ask the good question. I ask, what is the probability for the first qubit to be to have value 0? So you have the right to ask this question. Of course, since we have seen already in previous slides that this operator, this vector is this one. Oh, excuse me, this vector is a eigenvector corresponding to eigenvalue 0. But since you are in four-dimensional system, to ask this question, you have to. Oh my God! You have to pass from 2 by 2 matrix. You have to multiply by unity, because your question is related only to the first system. But your operator, the space is four-dimensional. You ask nothing about the second system. Therefore, you multiply tensor product with unity. Yes, and then this operator, it's four-dimensional. We have a question about probability according to formulas that I have written on the first slide. You have to, this question is, well, so, but since you multiply it by unity, this operator OA, it has two eigenvalues, 0 and 1, and each eigenvalue has a unique eigenvector. So for that operator, the spectra is simple, not degenerated. But for that operator, it is not. It is generated because since unity, okay, it does nothing. The eigenvalue of that product, they are still 0, but there are two now eigenvectors. Because here should be 0 in the first place. The second could be any, so you take 0 and 1. So we have this situation, and according to the formulas, that modified formulas that I have given in the first slide, this probability is equal to the sum, because of the eigenvalue 0 has multiplicity 2, and you compute easily this product, and you'll find that the probability 1/2. So this probability, the answer, quantum mechanics says use the probability that the first qubit is in the state 0 in the system of two qubits is 1/2. And since it is 1/2, it is clear that the second eigenvalue 1 also you can observe is the same probability. So if you do a lot of experiments measuring that, so you have a statistic, and statistic will be 50-50. Well, so but it is I haven't used this term before, but according to, because we didn't discuss too much the measurement, because the measurement is the most delicate part of the quantum mechanics. So I had no time to go to the subtleties and just mention that Born rule, but in fact it's more general things, because the philosophy is like that. You have your system in certain state, then you ask a question, what is the probability to find the system in another state? You measure, and the measurement made the collapse of, this is Copenhagen interpretation. After the measurement, your system will be in the state with a certain probability on which you ask in a question. So according to that, we started, the pre-measured state was like that. But after the measurement, your system will be in the state. You have to project your initial state. This is Born rule to the measured state, And this has to be a state that you have to normalize it anew, so you have to divide by the norm. And if you do again this simple calculation, you find that the post-measurement state is 0, 0. And this is a pure state after the measurement. Now assume that the second party, this is B party, so jargon of quantum information theory, they do not say A and B, say Alice and Bob, but I prefer less personalized terminology. So we have a question. Okay, this is a misprint. I have to ask, okay, this has to be written QB. So now Bob, B, would like to know what is the probability for his observable OB to be in that state. He has in that state 0, and he found the probability is 1. And what does it mean? That after the A measured this probability, its own observable, the observable of second party is fixed, is already given immediately, no probability, probability 1. And it is what was a puzzle for this famous author Einstein, Rosen, and Podolsky. They said that, and there is most important thing, that there is no time here. This happens immediately. So it could be, and the question by Einstein, naturally, the author of special relativity, is that how it could be, because there is a maximum limit of anything in the world. It should be light velocity, and what is going on? Why this could be immediately? There is no. So you have a action, certain action in your system which happens immediately, not after the time c multiplied by something. And it was called Einstein paradox, and Einstein said that it is impossible, and so quantum mechanics, it depends already on your characters. Einstein, people used to say that he was quite a gentle person. He doesn't say, many people after said that quantum mechanics is not correct. He said that it is not complete. There is something missing in this theory. It can't pretend to describe the nature completely. There is something behind of that. And he called this something hidden variable. So thus, there are some variables, notation by Einstein, this from that paper of 35. So in addition to the wave function, which is a basic object of quantum mechanics, there should be some parameter which we do not know. Nevertheless, these parameters to describe your system completely, the parameter should be somehow used. And since we know nothing about that parameter, again, this principle of complete ignorance that I used last lecture in describing the simple model of black holes, now it is assumed that this parameter is random. Of course, we do not know the probability distribution, but we know that it is random, and okay, as I have written here, it could be maybe learned in the future, maybe in the next century, okay. Nevertheless, but at the moment, this is something unknown, and we have to take this into account. It's a bit, if you would like, a simpler examples of this kind of philosophy. Assume that you calculate something in certain approximation, and you find that your quantity is okay. You have for its distribution just a peak, yes, and a quite sharp peak. But then you say, okay, it seems a bit strange. I have to take into account something else. For example, some noise. You take into account the noise in your peak. Okay, it broadened it. So you took into account something additional, and you'll get more information which you believe is more exact. Something like that. The same philosophy was used by Einstein and EPR, and so it is it is a sink, yes? And well, a lot of version of this hidden variable theory has been proposed and discussed. Nevertheless, none of them was more or less satisfactory. So this state of things was during almost 30 years, and when in '64, John Bell showed that the hidden variables are not possible. So they contradict to the certain basic facts of quantum mechanics. And this is called Bell theorem. And so the things that I said before, it is known as the E-pair paradox. Now, the solution of this paradox was proposed by John Bell in '64. And now I am going to describe shortly what is this solution. Well, first of all, it is convenient to have the situation more explicit and more contradictory. Bell used not the states that I used in my discussion of the E-pair paradox, but what is it in fact? This is if you use the terminology of spectroscopy, it is just if you think about not qubits, which is a new fashion, but just on spins, spin up and spin down, then you have to change a bit your setting. It's again in the framework of quantum mechanics. So instead of that state, it's just singlet in which both spins either up, both either down, so like in ferromagnet. He proposed to use another state. It's again Bell state. It was introduced by Bell. So this is a bit different states. So in each, your spins are always anti-parallel. So either up down or down up, with the same probability, because it is like that. So it is anti-parallel singlet. And now we use, instead of that variable that I used, just a bit different variable. They are simply related. This is just Pauli matrix that corresponds in quantum mechanics. This matrix describes precisely used precisely to describe the spin. Yes, and its eigenvalues plus and minus 1. This is precisely if you just use dimensionless situation, not to mention Planck constant. So spin will be either up, either down. So it's observable to measure spin. But of course, if you are trying to compute something related to the experiment, you have to replace plus minus 1, because by h bar over 2, these are real values. But we use the dimensionless units. Well, so this is a modification of the E-pair paradox or E-pair setting, but it was used many times before, nothing new in that point. And then, okay, and what is the next? This is just a scheme of the experiments that both, Einstein E-pair could use but didn't use. And in fact, what was proposed by Bell, in fact, he said that let's consider P0 meson, and it is known that its spin is 0, but there is a decay in two particles, positron and electron, with spins like that, and they go in opposite direction. So this is a scheme of the experiment. You use the source, the source of these entangled pairs, yes, and then they go in opposite direction, and there is a detector that measure plus or minus 1, and okay, and after that you measure how much you have the coincidence, how much you see the same thing. And this is like I said, that because of entanglement, you say once you measure the spin A, spin B is fixed. So there is no probability already. It's already deterministic, yes? And they try to find, in that case, by the way, in previous settings that I explained in a bit of details. You have your variable is either 0 and 1, but this is more picturesque picture. You say that it's up or down. So it is to measure how many times, provided that you measured system A, system B will be, in that case, in opposite state. So this, in that change of setting, this is you measure on system A, you measure spin up, then with probability 1, the spin B will be down. It's just the same calculations, but in a bit different, with different quantity. So this is a scheme of the experiment proposed by Bell. And now let's compute. This is, so the important modification of the E-pair setting, Bell said that why not I would like to consider not just spin ups and downs, say on the xz up or xz down, sigma 3, it's sigma z, but in any direction. But it is again simple quantum mechanics. It is known that you view 3 Pauli matrices, which are in fact the components, describe the components of spin, which is a 3-dimensional vector, in fact, yes, of operators, yes. So he proposed, and it's a simple thing, if you view these 3 sigmas, 1, 2, 3, in my first lecture I even shown what are matrices, and then you made this formal scalar product of the operator vector by a standard vector of unit length, yes. Then, according to the axiomatics of quantum mechanics, this means that you are going to measure your spin not in the direction of the z-axis, but in direction of vector A. So he proposed to make a more general situation, and then well, we have that. So now to measure, say, spin A, what is the probability to have spin A, this A in direction little a? What is the probability to find this situation? We have to use this operator for the system A and this operator for the system B. And it's easy to check. It's again simple exercise. Unfortunately, my course is short, so we can't do exercises, but this is very nice to go through all that. It's easy to check that this operator sigma square A, which is 2 by 2 matrix, in fact, it is written here. If you just insert explicit form of sigmas, you'll see that, and use these matrices. You'll find that for any A, the square of this matrix is 1. And what does it mean? That eigenvalues of this matrix should be again plus 1 or minus 1. What does it mean physically? That doesn't matter in which direction you measure your spin. The results of your experiments with a certain probability will be either 1 or minus 1. So not only if we up-down, when we are in the direction of third axis, it's always like that. And now the most serious new thing that Bell proposed, he said, let's measure this operator. So you have system A, allies. It has a variable sigma, the first one, then the second one, you had a product. So it's a certain variable that completely legitimate. You measure. You can ask this question, quantum mechanics. What is the expectation of that variable in the states that I written? This is anti-parallel singlet. So he proposed to consider this quantity, yes? And I remind you again that what is pi minus. Well, and then it's again, what does it mean? You have to recalculate. You repeat the calculations that I showed at the beginning, but not for 0, 1, but the sigma A. And if you compute, this is again a nice exercise in elementary quantum mechanics, you'll find that I. You'll find that the same situation like before. So the expectation of this product of two operators, one for A, second for B, it is always the expectation equal just the scalar product of these two vectors, yes? And but with minus, this is important. And so if your spins are parallel now, so we are back to the E pair situation, but not from 0, 1 plus 1 and minus 1. So our anti-parallel expectation is 1. Parallel expectation is 1, but parallel aligned, it is just minus 1. So the spins are strongly anti-correlated. Well, again, so we just nothing new. We just repeated the calculations of E pair in a bit general situation. Yes. So again, according to Bell, this result is incompatible with any hidden theory, whatever it could be, but it should be local. I have written local. That means that I'll show now what does it mean, because in principle there is unlocal hidden theory, and Bell says nothing about the unlocal things. It is still open, but it is not unlikely. It's unlikely, of course. Yes, okay. So we just pass to the argument of Bell. So what did he say? That okay, the first item, just repeat in fact the argument of Einstein to propose this idea of hidden variables. Now it is denoted by lambda, and this is a locality, as I said, that it is assumed, this is an assumption on the would-be hidden variable theory, that the measurement of A and B are independent. And this is indeed the explicit form of this locality axiom. Well, and whether they are hidden variable or not, we also can assume without loss of generality, in fact, just normalizing that this is what there are some functions that takes values 1 plus minus 1 for every system. In the E pair setting, it was just this variable OA times 1, which is just, 1, 0, 0, minus 1. And its eigenvalue again plus minus 1. So it is a hidden theory analog on the E pair quantities. Yes. So he assumes that there should be these functions A and B, which depends in E pair setting. In quantum mechanics setting, it was just each of them was function just of respective vector A and B. But here we have to add this hidden variable. Well, which by the idea Einstein, adding this variable, which is random variable as a certain probability distribution, we assume that these variables, they somehow describe completely the situation. And we assume, like in the E pair case, because this is a counterexample for the E pair case, we assume, and this is quite important, that when you have these two devices, and when the orientation is the same, then this anti-parallel, then A and B will have the opposite signs. So this is just precisely repeating the setting of E pair argument, but adding hidden variable. Well, and now this is a proof, just one page. Bell made the revolution in quantum mechanics, but by using it's a very short paper, absolutely clearly and concisely written. So let me it's written here, but let's discuss a bit. So we have according to this idea of hidden variable theory, now the expectation should be not just the product of that things, but should be averaged with respect to the value of hidden variable. Yes, we do not know this function rho, but okay, God knows. Well, and so the first line is just definition of the expectation in the local hidden variable theory. The second line of the first equation is already used that this variable, that if this vector B, A or B is the same for two parties, then this functions has to coincide up to the sign. Yes, so I replace B by A, but also with the, no, it's too early. So it is written below the. So what did I use to pass from the first line to the second line? I use this basic assumption about the values of these measured functions, that they are anti-parallel being aligned. Well, and now let's take a third vector C and write the same formula, replacing write the formula like the first one, but replacing B by C, subtract, and we'll get just first line. Now, I use the fact, I remind you that every variable, each function, either A, B, or capital A or capital B, they take values plus minus 1, so the square is 1. And you can easily check that the second line coincides with the first line if you just, the first term is written outside of the parentheses, but the second term will be equal because they are to be, you see, there is this factor and there is that factor, and their square is 1, therefore you will come to the first line. And now, okay, for the same reason, A squared is this function of two variables, b and lambda, but nevertheless square is 1, so the absolute value is 1, and that means that the parenthesis is not negative, yes, and these two functions by absolute value do not exceed 1, so I can just replace this, and rho is not negative, it's density of states, density of probability density, so you can write this inequality, just neglecting that, and okay, you see everything is written. But the first term, because rho is normalized to 1, integral of rho is 1, it's probability density, so just the first term in the parentheses now becomes 1, and the second is just the same definition, it is EBC, because it is with minus. So it is, I haven't written that, but let me write. So this is a Bell theorem that you see that AB minus AC satisfy this inequality BC. So these are just formal things. These are just numbers, functions, or scalar function, not operator like in quantum mechanics. Well, and this is a mathematical part of the Bell theorem. Now, let's check. Just next slide will show that this inequality, it is just assumption that there is some parameter, not quantum, but classical, but it is the idea of Einstein, that is something lambda, which is just random variable, maybe not just one, maybe it is a multi-component random variable, doesn't matter. I use nothing except that this is probability distribution of something, which is something, this is our hidden variables, yeah? So we just, let's check now whether this inequality is valid for the E-pair setting. These are 4 cases. You know, This is a table. So the first column does the values, some assumption on ABC. The second is this inequality. How does it look when you substitute the vectors written? And then you see whether it's correct or not. So if all 3B are parallel, then we have inequality is valid. Yeah? If you take A perpendicular to orthogonal to B, so you have this situation. This is A, say, this is B, and C is either here or here. So C coincides either with A or with B. Then again, nothing bad. But now I take C, which is just here. 45 degrees each. Then the equality is not valid. So we are done. We prove that in E-pair experience, the E-pair type experiment contradicts in certain setting. For the case when you do 3 measurements, you see already the contradiction. That means that, okay, the hidden variable theory is not impossible. And that means that quantum mechanics correlations are stronger than classical ones. So it is new theory. And well. And now it's just the comments. You know, if you look at any book or paper related to that, they are quite usually extensive because you need a lot of words to explain all the subtlety of the situation. There are philosophers, there are experimentalists, there are theoreticians, and there is a lot of interpretation of this experiment and this argument by Bell, but everybody agrees that after the Bell paper, local hidden variable theory is dead. So it is written in that conclusion. And first, of course, I have to mention the experiment for which Nobel Prize was given. This is Alan Aspect, and because his experiments was crucial. Because the first experience by Cruiser, it was very simple, and there were certain objections which even has a name. So after that experiment on 72 was published, there was a lot of objections about the proof on which extent this experiment is convincing. But there were some objections concerning the setting of the experiment. Yeah. So, and the most important moment was how to make this measurement simultaneous. Because you have to find the situation in which the distance between A and B is space-like using the special relativity language. So there could be no interaction between these two subsystems. And this simultaneity was quite non-simple, and the convincing experimental setting that exclude this conjunction was proposed by Aspect colleagues. So this is why this experiment, you may remember that the Nobel Prize was given for 3 persons. First, Cruiser, who was first in 72, made this experiment, thus starting the business, starting raising this question from a point of view experiment and providing some results, even not absolutely, ironclad. Yeah. Then there was 10 years later, there was Aspect who just proved precisely, and nobody objected that basically everything is made quite convincingly, and the contradiction was found. This inequality is not valid, in the setting. It was not precisely like I wrote. It's a bit more complicated, but nevertheless, it was a very nice trick how to exclude this objection about simultaneous situation. And then the third person that got a prize was Anton Selinger, but he did not discuss precisely EPR, just assuming that entanglement exists and is a good and important notion. He invented some procedure which is called quantum teleportation. And it was basically 100% on the states of these Bell states. So therefore, it was one of the first demonstration of utility of not just the abstract notion entanglement, but utility of this notion in quantum communications. And then later there was it was 95 already. There was a absolutely superb quantum computer algorithm by Peter Shor that by using again entanglement, he showed that you can propose the quantum algorithm that can break any code. And this is why some people are waiting that quantum computer can be constructed and somebody can break any code, in particular yours and mine, carte bleue. But on the other hand, the bankers, they are trying to understand how it could be avoided. Well, but so it is the first conclusion is negative, but there is a positive one which seems more important. So the nature is not local, in fact, and this is quite serious revolutionary statement, because after it comes to it dates back maybe to Aristotle, but of course Newton and then classics of classical mechanics and then Einstein in special relativity showed that theory is nature is local, that any action has to propagate with a certain velocity, not exceeding the speed velocity. Yes, light speed. Yes. So it was serious, support for quantum mechanics, and there is I added one more thing, which is also in a way new, and we are going to discuss on this in next lecture. There is one more demonstration of that non-locality is just if you pass from few-body problem. Almost all these discussions that I had before, in large part of quantum information theory, it deals with the spins. And so there is no question about symmetry, anti-symmetry of your wave function, yeah? But if you pass to real many-body system, we know quite well that there are in fact basically two situations, bosons and fermions. And because of anti-symmetrization, you immediately see that so it's very simple to get entanglement system, because if you ask myself how to create entanglement experimentally, the answer is generically just by forcing part of the system interact. So you use them interacting, they become entangled, and then you switch off interaction, and they are living like that. Like in the Bell experiment, there was P0 meson in which positron and electron lived before. After the decay, they go apart, but they are already after interaction, they are entangled. So it's not only way to make subsystem entangled, but most natural and physical way, this interaction, yes? But for fermions, for example, you can use you have two particles, yes? Psi1 on X, psi. You have system psi1 of two. You have two particle system, and it is one particle states, but you can construct very simple. It's like, by the way, the states that I use, the Bell state. If you write like that, minus psi 1 x2. Yes, this will be the already not this state. It's just two quantum particles without symmetry, but in fact it is not two physical. Yeah, you have to assume that they are either symmetric or anti-symmetric, like here. Anti-symmetry, these are fermions, and this is already superposition. So every term is a product. That means the particles do not interact. Otherwise, it will be just a function, a unique function, okay, of two variables. If two fermions are anti-symmetric. But here, yeah, they do not interact. And nevertheless, just because of requirement to be anti-symmetric, it's already entangled. So free fermions, even being free, are already entangled. So it is another reason to be in that situation. Well, and this is a bit long text. I'm not sure that, but this is about the causality, because it was, in fact, the main objection by Einstein that we have problem with causality because, according to special relativity, any action, any change which some part of the system could produce in another part, it propagates with this velocity not bigger than the light. Yes. So, and this is one of possible explanation, not unique. But myself, I somehow liked it more that you have to just recognize that this there is no physical actions to get this collapse of this is in fact the question about the collapse of wave function. This is a basic postulate of Copenhagen interpretation. So it is somehow not causal and not causal. And this is myself. I have a very simple case, which is in fact the question for the students that started to study special relativity. And the standard question is as follows. So let's take a spotlight, very strong, and take a cylinder of very large radius, and now there is a beam of light. And if you rotate this spotlight fast enough, and if the radius is large enough, then the speed of this light spot could be bigger than the speed of light. Is this a contradiction to quantum mechanics, to special relativity? No, because there is no. It is just the how to say. I forgot the word. Как тень. Как сказать тень? Shadow. Oh yeah. This is just the spot. There is no physical things going on. So it is quite possible and no contradiction. And this is something like that. So the entanglement is a bit ideal things. So you can't see it itself or collapse of wave function. It just happens outside of experience. You see, of the experiment, you see just the result. I am not sure that I explained it, coherently enough, that point of view. But okay, this is one of the interpretation of the Bell's situation. So to say contradiction between E pair and Bell that somehow explains that there is no harm in that it's quite possible because it's a bit, outside of the, it's not like it is written, not some change in the, physical action. It's a bit different story. So in a way, this kind of interpretation corresponds to the point of view which was used, in fact, most of physicists that are doing quantum mechanics, not itself or, anything related to the quantum world, any calculations, so this motto looks like that: shut up and calculate. So it's too much philosophy. Most of physicists used to say it's too much philosophy. There is, quantum mechanics is absolutely clear-cut set of axioms. And using these axioms, you calculate and you get the result, which are in complete, agreement with the experiment. So don't think too much about philosophy. And in a way, this is a kind of best possible that this part of physical community could produce. There are other explanations with a lot of, even philosophers, and a lot of them that are trying to understand what is going on. Just like in the uncertainty relations, there is a lot of speculations related to these important facts of quantum mechanics, but okay, this is a situation possible. There are still, there are still people that are not satisfied with quantum mechanics. They are proposing certain other theories, but so far, okay, they are not so successful as quantum mechanics, and people keep to the quantum mechanics like something that is better of all possible. It's a bit pragmatic point of view, but nevertheless. Okay, if there are questions, I am ready to answer related to this particular. Yeah, please. Now I'll continue the course, and today we are going to discuss this third item of the course, third item of the program. So it will be an introduction for the case that I mentioned in passing just on the first lecture. So, but you remember last lecture we studied just 2 qubits. How do they behave? What is their evolution? In fact, not 2 because there was an environment. So there are many, but we are interested in 2. But already in the first lecture, I mentioned the system in which you deal not with qubits, but with more complex, multidimensional quantum system. It was this toy model of black hole radiation. But here we are going indeed to consider the general case. So it is a picture. You have some environment, a quite big system B, and inside you have a system A, which, because of that setting, quite often is called just a block. You have a big system. Inside you have a block, which is not 1, 2, 3, but already also there is a lot of quantum object, particle spins. In both systems there is a lot, but in environment much more than in the block. So it is intuitive heuristic setting. But in the topics that I am going to discuss, first I just say and remind you quite shortly what is entanglement entropy in that setting. Then, general setting for the extended systems. And then I'll give the short review of results for translation invariant systems. These are mostly spin chains, one-dimensional system of spins, quite long chain. You take a block inside, and then you try to understand what is going on. What are quantum correlations between A and the rest of B. And then I'll show that free fermions it's already, there was a hint here. Free fermions are quite good, despite that a bit toy model. And you can see almost anything that you see in this one-dimensional speed chain. You can see in Fermi gas even in clearer way. So, and then this free fermions, I'll just describe general setting. The most serious distinction between the spin chain in free fermion system is that free fermion systems, they are simpler. Being entanglement, you have an entanglement as I explained it. And because of that, you can find not only you can analyze not only one-dimensional systems like spin chains, but multidimensionals also. And this is the important advantage of that despite toy model. Well, and the first, of course, again, the entropy, and in that place maybe I wrote something that maybe I had to mention the first lectures that in classic, I did mention here Clausius, who was the first introducing the entropy in the setting of classical thermodynamics as a measure of heat which system could accept. But I am just, for microscopic setting, it was worked out, as we know quite well, by Boltzmann and Gibbs, and the analogous quantity was invented anew by Claude Shannon in information theory. By the way, he didn't know about this notion of entropy, etc., and he created, you may know, he created classical information theory in late 40s and early 50s. And once he discussed his results with von Neumann said the quantities that he used is just the entropy. And this is how the link was established. And well, as for quantum physics, we have discussed already. I am just repeating. So in quantum system it is not the measure of randomness, so to say, but it is a kind of measure of quantum randomness. The quantum randomness, what is it? Is a mixture. The purely quantum are pure states. Mixed states, this is a classical mixture of quantum states. It's a bit intermediate situation. And the entropy, as I mentioned in the first lecture, could measure this, the amount of mixedness and amount of entanglement. Yes, and the most interesting is not just the entropy of a whole system, which is quite often pure. For example, start from the universe. It's pure state, like for Gibbs. His basic ensemble in classical statistical mechanics was microcanonical ensemble when the system is just fixed energy. Yes? So, but it turns out that quite interesting is the entanglement entropy, which you start from, say, bipartite system. It could be even more parties. Then you take the corresponding density matrix, and yes, and then okay, this is yes, and then you trace out the degrees of freedom on B. You get the reduced density matrix, and you calculate the corresponding quantum mechanical von Neumann entropy. Well, on the last lecture, I mentioned other quantifiers. It was, I remind you, negativity, concurrence, and quantum discord. They are, in a way, more exact and more up to the point. But the problem is that they are so complex defined that you can't even hope to calculate these quantifiers for system that contains a lot of qubits. But we are going to discuss precisely that situation. And this is, by the way, one of these technical difficulties is quantum information theory, because take statistical mechanics. I mentioned in the first lectures that the reduced density matrix, it is a generalization of the correlation function of statistical mechanics. If you have two spins, we say it's a two-point correlation function. But in fact, this reduced density matrix, it was first realized by in particular situation, by Dirac and Landau. Well, but if we are dealing with, say, 100 or thousands of qubits, then it's hopeless to compute the concurrence or negativity. It's too complicated. So we are going back to the simplest quantifier, the entanglement entropy, because of technical difficulties to calculate other quantifiers. Well, so at that lecture I will use the entanglement entropy as a quantifier only. Yes. Well, and as I said, okay, intuitively, what we are going to do? To make things concrete, we assume that our system, this big system, blue system B, it lives in a three-dimensional space, in our real space, yes? And the subsystem, the block, it is a part of that system. It's a sub-block lambda. So all the system will be denoted by omega geometrically. See, just a cube. Yes? And subsystem is a subcube, and their linear sizes, just in the cubic side lengths, they will be related in this a bit heuristic way. So we are now studying not like the previous lecture when L was equal to 2, but it is big, it's big comparing to, I assume that there is a certain length in the space. For example, you are on the lattice. There is, of course, the distance between two nodes of the lattice, but we just assume that it is one, dimensionless units. Therefore, the number of particles or objects in the block is big, but nevertheless is much less than the number of objects in the whole universe, which is n. Well, and what we are going to study? We are going to study that in that asymptotic regime, we would like to study the asymptotic form of the entanglement entropy. Yes, and this problem arises in a number of fields of physics. I just mentioned a few. The first, it was somehow found in black holes, and we already mentioned in passing this situation in the second lecture. I showed that it is a toy model of black holes, and by the way, over there we use this inequality already. Different version of this inequality, yes. So, but since that, it was in the early 70s. I'll show certain authors on the next slide. So the first field in which it appeared was the black holes. Then, this was quantum statistical mechanics, because it turns out that the so-called quantum phase transitions that happens not because of varying of temperature, but varying your system is many-body quantum, and you vary other parameters, external field, coupling constant, something else. Then you'll find that even in one-dimensional system, because generally, if temperature is not zero, then there are no phase transition in one-dimensional system, short range. But at zero temperature, in ground state, even in one-dimensional case, you can find a phase transition, and this is called quantum phase transition, yes? Yes, and recently there was another subject, quite, by the way, active. There was a question, okay, how to reach the equilibrium? In classical mechanics, look at any book, you see that equilibrium just because of exchange of energy or particles between the system and the environment. But if you take just a moment. Yes, if your system is closed, like the whole universe, yes, so there is no environment, and therefore the question, how do the system reach the equilibrium? And the idea that was put forward by Charles Deutsch, that it is because, okay, our system being closed, it is in quite excited states usually. It's analog of temperature. And because of that, there should be some kind of equilibration or, as a thermalization. And there is a lot of papers, including the numerical results, etc., showing that this conjecture is quite natural. It is even, there is a name even for that conjecture and for corresponding results. It's called ETH, entanglement, thermalization, hypothesis. Well, so we see that it touched, so because of entanglement now, not because of exchange with the external world, which doesn't exist if you are in the closed system. So, but there is a quantum reason, quantum randomness instead of environment randomness somehow, strive the system for the thermalized, for the somehow equilibrium state. And all of these things, they are based on the calculation of the entropy, etc. So there is enormous amount of work on that subject, and I am just a little tiny portion of that going to discuss. So these are the first paragraph is some names that was related to the initial and in the next after initial stage of this field. So the first was Bekenstein, who found, so to say, area law, which I'll show the next. That in the black holes, he found that I am a bit ahead of. So Bekenstein proposed a quite intuitive and not on the first glance reasonable argument to show that if you have a black hole and if you calculate its entropy, it was Hawking who said first that we have to apply quantum thermodynamics to the black hole. But it will be proportional, not the volume like classical mechanics taught us, but it will be proportional to the surface of the, and this surface is just, this is how to say, event horizon. Yeah. And then there were calculation in quantum field theory, a lot of authors. And then was John Cardy had started a lot of calculations with diversive results for conformal field theory, quantum field change, but one-dimensional systems. And this is just to mention a few, because there are hundreds of authors and papers. Now the question is, what does it mean, this evident but heuristic inequality? How do you implement this inequality? And the simplest way is the following. So you keep your block L fixed, and you do macroscopic limit with respect to n. So you compute first, I'll show on the next, you compute first in this finite system, you compute the entanglement entropy. Then you make macroscopic limit. That means the omega big domain expanded to the whole space, and the block is still fixed. And then, upon given this macroscopic limit, you start you assume that it is large. L is large. So this is a more or less simplest implementation of this inequality. So instead of that, which is a bit more complex and not always clear cut, you just you just use this setting. So as I said, you do first this limit, and then you study the asymptotic with respect to the second parameter. And I'm going to change my notation. Before, rho AB was just the density matrix of bipartite system consisting of two more or less on the same footing system, like two spins, two qubits. But now my A is a block and my B is the environment. So I change notation. Instead of these three, instead of rho AB, now I write rho omega, just indicating that this is a density matrix of the whole big thing. Then if I am computing having rho omega, I have to compute the reduced density matrix. So I have to trace out with respect to degrees of freedom outside of block. So my system is like that. And my block is here. So this is, as I said, this is all these things is omega. and this is the subcube is lambda. Yes, and so I trace out the degrees of freedom that belong to the rest of the system. I get reduced density matrix, which I denote now subindex lambda omega, and the corresponding entropy, the whole system, and the entanglement entropy. Well, with these notations, so you compute these things. It depends, this S lambda omega, this is your entanglement entropy, but following this, this regime, this setting, we do the limit omega to the whole space, and the result we will denote S subindex lambda, and okay, it was a result of very many calculations on various models with various settings, but the results could be summarized as following. So the first and most impressive, okay, in a certain sense, the first. So that the asymptotic is like that. You see, it's called area law because you see that if you are, and there are conditions. So if you assume that the whole omega is in the ground state, there is certain Hamiltonian which is not present, but of course, if we are serious, we have to dealing with the system, quantum or classical, we have to first of all to know its Hamiltonian. So there is a Hamiltonian, you know, and your system, big system, your universe in the ground state, and if this ground state is not critical, that means that there is no phase transition, quantum phase transition in your system, then it turns out that the entanglement entropy is proportional to the surface of your subsystem. And it's called area law. It was first proposed with a constant which is expressed via parameters of black hole, fundamental parameters, charge, cosmological constant, etc., was proposed by Bekenstein and then made much more rigorous, so to say, by Hawking in 73, 74. And then, more or less recently, it was understood that in quite general but one-dimensional systems, you have which is in ground state, you will have this area law if the spectrum of your system has a gap between ground state and the excited states. And many body result, quite serious. It's Michael Hastings who proved this theorem. So these are general results, but we will see much more. It is just a kind of summary of very many papers and discussions. Now, the second one turns out that there are situations when this area law is depending on your mentality. You can say they violated or just enhanced. So you have an additional log. So without log, which I wrote in boldface, you are you have a area law. And here there is a bit more. Not too much because log is quite slow function, slow growing, but nevertheless, there is a difference. By the way, there are certain systems that I'll discuss in the next lecture with disorder, and starting to think, to work, myself and colleagues of mine, we did a lot of numerics, and it's you have to do quite extensive calculations, numerical, to recognize the log, especially in dimension bigger than 1, when you have for example, two-dimensional case. Real law is just linear, and the log is just a bit of more, and it is not simple to detect numerically. You need the big samples, a lot of Well, and the third, maybe I have to mention the first, because traditionally, which we know since our student times, that the entropy, take any book in quantum mechanics, starting from Gibbs, the entropy should be proportional to the volume. It's extensive quantity. Yes, and in new understanding of these things, in quantum systems, we say that we have a volume law, which is classical things, in fact, and the quantum case also. If your system in a mixed states, first of all, in a Gibbs states at zero, not zero temperature, or, and it is new, it is just because of this new field of studying this entanglement thermodynamic hypothesis, that it could be in the pure state, but not ground state, but in high enough at the spectrum. And this is still not completely clarified. There is a lot of arguments, heuristic, numerical, but still no, and even proof in certain particular models, but not more or less generally, still not proven. Well, now we have three types of asymptotics formulas, and now in which cases? The first, all the three are, for d equal 1, are more or less well done in the dimension 1. As I said, mostly these are spin chains, one-dimensional systems of spins. Yes, and their entanglement is the result of interaction between spins. And as for d more than 1, you can see that my formulas are written for any fixed dimension. These are mostly either conjectured or they are calculations that are not completely, well done. There are replicas over there. There is no still proof that replicas are good enough in that case. But rigorously, more or less rigorously, it is established for all these three asymptotics for the free fermions, translation invariant fermions. Again, this I mentioned already. This model maybe looks a bit oversimplified, but it is doable. It's not last things in the theoretical physics to be able to compute something. Yeah, so it is one of the reasons I had mentioned already that why free fermions is worth to study, because you can see all three cases. You can see the mechanism that is behind. Well, and now let me say shortly about quite general things about free fermions. I believe everybody knows what are free fermions. These are, this is quantum mechanical, this is second quantization formalism. What do you have? You have a, now your omega is still, but it is a cube on the d-dimensional lattice, and for every side of the lattice you attach the operator Cj, okay, and this is just an operator, and there is a Hermitian conjugate with here I denote, this is tradition, I denote by cross, and they are anti-commuting. So you have a collection of operators. The number of them is equal to the number of sides on your omega, and you write this quadratic form in operators. It's easy to check that if this I haven't written that the matrix is Hermitian, and this because of matrix is Hermitian, this, oh my God, this H hat is also a Hermitian operator, but it acts in very many dimensional space. In fact, the dimension of space is a so-called Fock space. It's the dimension on 2 to the power omega, so it's quite big. While this matrix, you see, it is indexed by the sides of omega, so it is just the operator of omega, the number of sides in omega. I denoted just the absolute value of omega, so it is much less dimension space, but because of the fact that fermions are free, in fact, all the physical quantities related to that system for example, electron in the metal, that since the Bloch in 1925, good model to study the conductivity, a lot of things in metals. So it is dimension much less, and nevertheless, this one body, it's called one body Hamiltonian, it determines all the properties of the fermions, yes? Yeah, and then just because this is quadratic form of Fermi operators, and since the Bogolyubov in the late 40s proposed very efficient method how to diagonalize this big operator, it's called Bogolyubov transformation. And okay, I will not enter in the specifics there, more or less standard. Nevertheless, by using this formalism, you can find the formula for the entanglement entropy. It is written here. Let me explain, because there is first of all, okay, let's start from you start from how to say, okay. First, there is a function, excuse me, h. It is just a simple function, you see? In fact, this is Shannon entropy of binary distribution. Well, you have this function h, function 8, and then what do? This is your one-body Hamiltonian. You write this operator, which is in fact operator form of Fermi distribution, which we know, everybody knows. So it is again operator acting in this omega dimensional space. Well, and then what do? You do very serious thing. This operator is defined. It's a matrix. It's a matrix of the size this n hat omega. This is a matrix the size omega times omega. So it is a big matrix. Yes, and then you just take a block of that matrix of the size which is much less. And this procedure, it's just linear algebra. You have a big matrix, and you take a block inside, and you forget about anything else outside. It's called, in linear algebra, it's called restriction. You have big matrix, then you restrict yourself to the matrix, to the entries inside this sub-block, and this is called restriction of, this is a restriction, and usually to the lambda. So you just cut out you throw out everything outside. And this is what you do. So as I said, h omega determine any possible quantity related to free fermions. And in fact, this is via this operator. So you have h omega. Now you compute this operator. You do restriction. You'll get the operator, the matrix lambda lambda, which I denoted subindex lambda omega. And so this is a Hermitian operator matrix as well. So you compute the function. This is again Hermitian operator because function is real valued. And now you take trace. You make trace. And this is quite nice formula, because when you would like to compute something about interacting, say, fermions, the first question is you have just general definition of entanglement entropy, this big Fock space. You do not know what to do next, just next step. Here we have a quite nice formula which allows us to compute a lot, not necessarily. For example, you can use these similar formulas to compute, say, conductivity of the metal, which is basic quantity, and many others, yes? But myself, I would like to draw your attention that for the special case, this is for non-zero temperature, yes? This is Fermi distribution, just standard things. Now, if we are at zero temperature, we have to take temperature. You can convince yourself easily that it is just, okay, the theta is just a Heaviside function. This is Fermi step, yeah? We know that the function like that. This is Fermi, just a parameter, energy, and here this theta. So it is just function which is one if your energy of your fermion below the Fermi energy and 0 outside. And this is called Fermi sphere. In fact, Fermi ball, yes? And because of fermions, yes? So we have at 0 temperature, which is the most interesting case for us, because, as I said before, this area law and enhancement area law, they happened only at 0 temperature. So we have to use this formula for t equals 0, for 0 temperature. We have to use this formula in which n hat is just this operator, which is called Fermi projection. Yes, it is written here. So in fact, what is the p omega? Let me write maybe to make more clear the situation. Yes, it is just you have a you have your operator h omega. There are eigenvalues, corresponding eigenfunctions, and the p omega e Fermi is the sum over all energy less than or equal Fermi energy of the corresponding. So this is so all the states below Fermi energy are occupied, outside the Fermi energy are free. And so everything is completely, explicitly written. And now let's use this motto: shut up and calculate. You have to calculate things, yeah? And so if you do that, if you have a translation invariant case, in translation invariant case, your operator, one body operator, so we have this formula, yes, for the 0 temperature, and I just explain it once more, what is it? And we have this nice conclusion that we have a many-body problem, and always this is a complex things to do, but here we reduced everything to spectral analysis, in fact, of this H omega operator. Of course, it's very big, but nevertheless, it's already one-body problem. It's often doable, yes? And so what do we do? In translation invariant case, what is it? In that case, this matrix, one-body operator, is you have to replace by depends on the difference of indices. No, because of, or like people do in quantum metal theory, it could be periodic with certain period, but it is already, nevertheless, it's already translation invariant, yes? So this is a basic things. So this is, and in that case, the eigenstates of this, they are just, some normalization factor, which I do not write. Just plane waves, yes? K, J, X. X belongs to the omega. And K, this is what is it? Is momentum. Or maybe sometimes it's called quasi-momentum of your electron, yeah? So explicitly written, quite simple eigenfunctions. You deal with exponents. You do, in fact, you do the Fourier analysis, and you find, but the corresponding arguments, unfortunately, quite involved. To prove, for example, it's already To prove, for example, this formula in d bigger than 1, you have to use quite a heavy tool of modern analysis, so-called hard analysis, so-called pseudo-differential operators, etc., etc. From the point of view corresponding mathematics, quite involved things. And nevertheless, by using the technique of modern spectral theory, operator theory, you can you can do this. So first of all, you can make the limit, because these formulas above, they are, oh, what is going on? Nevertheless, all the formulas, they contain omega. The first thing that I have to do, according to this prescription, I have to take macroscopically. This could be done. Roughly speaking, it's always valid if your Hamiltonian, these entries, even not being translation variant, decay fast enough. And then, of course, you can do the macroscopic limit. After that, you are already, one body operator is already defined in the whole space. This is real Fourier analysis. You are involved in that, you are doing, and you arrive to the area law with a certain constant, which is explicitly calculable, but in general it's quite complex, I do not write. And again, so we have a, so it is, I am not here. Excuse me, oh, it's good. So now we have the area law, but now, okay, we deal with the spectrum of this operator. So it just say three-dimensional matrix, depending on the difference of arguments, called, by the way, Toeplitz matrix in mathematics. And you compute these things, you obtain the formula for the, but for that formula to be valid, you have to assume this parameter, Fermi energy. It's free parameter. In many body interacting fermions, it is defined in quite complex way, Fermi, depends on the density of electrons, etc. But in this one embodied setting, it is a free parameter. So if I put this parameter in the gap, assume that spectrum of H, already H, which is the limit omega to the d of H omega, the spectrum is just the line on real. Operator is Hermitian, so you have the Fermi energy here. If the spectrum is like that, there is a gap in the spectrum. Then if your Fermi energy in the gap, you have a real law with the explicitly calculable constant. If, on contrary, you set your Fermi energy inside of the spectrum, then you'll get enhanced area law. So you get additional log to the area law, yeah? And when you get the volume law, quite known standard things, it is if temperature is positive. And this is a classical result written in any book on solid state or statistical mechanics. That you have the free fermions, you would like to compute the entropy at zero temperature, for non-zero temperature, you'll get that. In solid state physics, myself, I have the training. Nobody calculated before this stuff. Nobody was interested in zero temperature entropy. Okay, conductivity, of course, it's important, but not entropy. It turns out that entropy is special. It has this real law. Well, and if you just a bit mathematical, taste, you can easily find that you get volume law, not necessarily for this, it is physics, of course, fermions. But if you are a mathematician, you can find quite easily that not necessarily to have this function you can take any, for example, once differentiable function, you can compute operator of that function, not of this special exponent, and you get again volume law. So the question why we have a real law or enhanced real law, that we are dealing with that function. There is a jump. So mathematical mechanism of free fermions to get either a real law or even enhanced area law, it's to deal with that function which is not, smooth enough. Okay, and this is all things for today. And last lecture, I'll start from explaining what is a localization. Okay, it will be about real disordered system. First, it will be explanation of localization, then the results concerning the entropy. Oh, excuse me, I am a bit late today.